Well, thank you, Marina, for the introduction, and to all the organizers for putting together this program, especially at these very difficult times. And I'm going to try to add myself a little bit of entertainment to this program. Hopefully, I'll describe some work of interest to both harmonic analysts and number theorists. And this is joint work with my postdoc, Bartosz Langowski from Indiana University. Please, at any point, don't feel shy to interrupt me. I'll try to pause and ask for questions occasionally, but I think I only have about 16 or 17 slides, if I'm not mistaken, and we should have plenty of time, for questions both during the talk and also afterwards. All right, so let me describe the topic. So I'm going to start with an exponential sum, which I denote by S of x. S could come from the word sum, for example. So I'll have a subset of lattice points called capital A, and I'm going to have a bunch of weights, the little ans. They are complex numbers, and then I have this exponential sum, which is the sum of all these weighted waves. The second thing that I'd like to consider is a smooth hypersurface. And you can think about the sphere, the cone, the cylinder, the paraboloid, etc. And the surface measure associated, the natural surface measure associated with the surface sigma is going to be denoted by d sigma. And whatever exponential sum you consider, there is this basic estimate, the L2 orthogonality, which says that the L2 norm of the exponential sum on the torus, and the torus is identified with the 0 onto the d. This L2 norm is equal, in fact, to the L2 norm of the weights. And then you can start asking various questions. I'm just listing some of them. You could ask somewhat informally whether S of x can be large on a large subset of sigma, or you could ask for what values of p the integral of this exponential sum to the power p on the hypersurface sigma with respect to the surface mesh is comparable to the LP norm on the torus with respect to the Lebesgue measure dx, or if you want, maybe you can just look at less than or equal. So is there a scenario where S of x could have a larger moment on a submanifold than the initial moment? You could also phrase the question in part 3 as a square root cancellation type question. If these waves interact with each other in a sort of random way, if you want, then the typical value of the sum S of x, the typical magnitude, will be roughly the little L2 norm of A. And maybe there are values of P for which you can have such a square root cancellation. So for P equals, I should say that the larger the value of P is because of Hölder's inequality, the harder it is for this square root cancellation to happen. So sigma has finite measures, so keep in mind there is a Hölder's inequality that relates various moments. Or you could rephrase 3 in a slightly softer way, but essentially equivalent way if you want. Namely, you could compare the pth moment of S, not with the little L2 norm, but with this quantity on the right that is in fact equal to the L2 norm if the sequence is constant. And I should also say that all these questions in most cases are already interesting and non-trivial, even for the constant sequence an equals 1. Okay, any question so far?
What are the capital A usually in your mind?
Well, I'm going to give you the examples. So I'll get to
Okay.
example 1. So I'll describe, I mean, okay, so these questions are sometimes easy if A is a whole block of integers, you know, perhaps
Right.
the whole cube or something, but the interest lies in the case when A itself lies on some manifold. So the first example, that actually has motivated initially most of our work, and we spent some time thinking about this last summer during the pandemic, is the example of lattice points on dilates of the sphere. So I have an upper script S, if you look at the top of the screen, to remind ourselves that we deal with a sphere. And this is the sphere of a radius square root of n. And I'm looking at the lattice points on such spheres. You let square root of n or n go to infinity, and trying to understand what happens to the moments of such exponential sums. There's this conjecture by Bourgain and Rudnick. It may have been asked before them, but they sort of formulated it and produced some positive evidence in its direction, which says the following: that if you have, let's say, real analytic hypersurface with non-zero Gaussian curvature and surface measure sigma, then the conjecture says that the L2 norm of the exponential sums restricted to this hypersurface have to be in fact comparable with the L2 norm of AN. So notice that there is a double inequality there. There's no n to the epsilon losses. Okay. Now, the first observation is that L2, the big L2, cannot be replaced with a larger P if you insist on the inequality on the right to hold true. You can make P larger, you know, for the left inequality, because the LP norm, as explained earlier, only gets larger. But there's a simple example that shows that the inequality on the right really needs L2. So that's something to keep in mind for the other examples that we will discuss. So, all right, it's L2. You think the problem should be easy. How complicated could L2 be? Well, it turns out it's a very complicated problem. What's the motivation? Well, other than the, let's say, intrinsic motivation, there is, you know, this is part of a much larger circle of problems that have been analyzed for many years. You have a manifold, let's say compact manifold, such as the torus. You look at the Laplacian, you look at the typical eigenfunction, and you want to study perhaps the zero sets, the so-called nodal sets of those eigenfunctions, or you want to understand how those eigenfunctions concentrate on various manifolds, etc. And it turns out that these exponential sums that we are looking at are nothing else than the eigenfunctions for the Laplacian on the tori. So Bourgain and Rudnick wrote a very beautiful paper that I recommend everybody to have a look at. It's very inspiring. You know, one of those Bourgain papers that you know, you read for many years, many times, and you still discover something new and interesting, even perhaps after understanding or feeling like you understand almost everything. So it's a very long paper, very rich, and also very readable. And what they do is they solve the conjecture for d equals 2 and d equals 3 by essentially using the Fourier expansion of you know, for the surface measure for this for a typical hypersurface sigma. So yeah, there's this formula at the bottom of the screen that I don't want to comment too much on, except that there is a decay, sort of magnitude, and there's also the oscillatory part that comes from here. Now, for d equals 2, so you're dealing with the case of the circle. The decay, if you plug in d equals 2 there, you get a decay of -1/2. That decay suffices. It also suffices if you're interested in proving the right inequality for d equals 3, and if you allow yourself some logarithmic loss. And that proof, or these proofs, I should say, are very, very immediate. They are exactly what you expect. You take the square on both sides, you expand the sum, and you're left with some rather easy computations just using the decay. Now, things are much, much more complicated in 3 dimensions. And most of their paper, about 30 plus pages, is spent with removing this logarithmic loss in 3 dimensions. And since I'm advertising this paper, I'd like to say a few words about their argument. So I'd split the argument perhaps in 3 parts or 3 ingredients. The first thing that they use is the distribution, things about the distribution of lattice points on dilates of the sphere. Now, the sphere is a weird creature when it comes to lattice points. It doesn't quite contain the so-called or quote-unquote correct number of lattice points. The sphere, then the number you'd expect, they are spread in an uneven fashion. There are gaps, in the distribution and so on. Now, they don't use, or they don't need things that are cutting edge technology, but they do use things that are highly non-trivial. And one of them is the fact that, for example, if you cover, let's see if I can draw a picture. This is the sphere. You cover it with small caps. The radius of the sphere is square root of n, and you cover it with so let's say square root of n is equal to r, the radius of the sphere. Then you cover it with caps of diameter roughly r to 1/2, and heuristically expect each cap in an idealized way or world, you'd expect each cap to contain about one lattice point. And this is because the sphere of radius r contains not r squared lattice points. It contains roughly r lattice points, and r is n to 1/2. This number shows up on the right. And again, if every such cap would contain exactly 1 point, then by squaring 1 and summing up these contributions, given the fact that you have exactly n to 1/2 caps, you'd expect to get something like this. But of course, the points are distributed unevenly, and so this distribution is something that, or the proof of this distribution result needs a bit of attention. All right, the second thing that they are using is a certain normal form representation for the oscillatory part. So let me go back to the previous slide, if you can see it. So here at the bottom, you have the cosine part, which accounts for some rather critical oscillations. And those oscillations are quantified in a slightly better way by doing certain changes, analytic changes of variables. Now, what's interesting is that if you do these changes of variables, of course, you completely destroy the initial rigid lattice structure of the lattice points on the sphere. But what you preserve at the end is a certain minimal separation. So maybe the points are no longer lattice points, but they're not going to clump together too much. All right, and the last key ingredient is what I call a power saving. So what you do with the new points, with these, initially you start with the lattice points, you transform them, so you get a bunch of points that you might call x and y, and you have a sort of bilinear version of or part of the argument, which forces you to estimate exponential sums of this sort. And all you know about capital X and Y is that it consists of sufficiently separated points inside 0, 1. And what's the explanation of this result? Well, how many such points can you have? Right? The maximum cardinality of both X and Y is about beta to 1/2. If you multiply those together, you get beta. So without minus kappa, the estimate would be trivial. The power saving comes from the fact that there is some positive k. Okay. Any questions so far? So hopefully I got your interest in this paper. I will say that the Bourgain argument does not really use too much about the lattice structure of the points on the sphere. Essentially, it extends rather smoothly to the case when you have some random points on the sphere that have the correct numerology or statistics. So I explained earlier the fact that we would like every cap C alpha to have roughly 1 point, perhaps in some sort of an average sense. Well, the random points would certainly do that. There is also this affine change of coordinate or analytic change of coordinates that completely distorts the lattice structure. They also construct examples to show that this, I don't want to call it cheap approach, it's an approach that takes 30 plus pages and it's highly non-trivial, but this simplified, let's say, approach is failing in high enough dimensions. So if you, for example, want to prove the conjecture in dimension 8, then you're going to have to take much more advantage of the fact that the points lie, the points are lattice points. Okay. Now the case d equals 4 is significantly harder than d equals 3. And part of the difficulty is the fact, going back to the previous slide, is the fact that you're no longer happy with a power saving. For d equals 3, the kappa greater than 0 is enough. You don't care about what the gain kappa really is. In higher dimensions, you have to keep much better track of the saving, because in the end, you're not trying to remove a log of n, you're going to try to remove a power of n from the loss that comes by only using the decay of the Fourier transform as opposed to the decay and the oscillation. Right, so questions before I move on. Okay, so d equals 4 is difficult, but there are questions even in 2 dimensions, and we have one page at the end of our paper proving this little cute result. It's a result that dwells on a conjecture by Ciprian and Granville. This conjecture says the following: if you have the circle of a certain radius, let's say square root of n, we know that this circle doesn't contain too many lattice points. There's at most n to the epsilon of them. But an interesting variant of that would be to understand what's the maximum number of points that there are on an arc of length r, if r is the radius, r to the power gamma. It's not very difficult to show that if gamma is 1/3, this goes back to the work of Jarnik about a century ago or so. If gamma is 1/3, then there is at most one or two, I forgot, but O of 1 lattice points on every arc. Ciprian and Cordoba have proved that if gamma is less than 1/2, then you have the same result as O of 1 many points independent of R. And the Ciprian and Granville have made the conjecture that, in fact, for any arc of length, the radius to the power gamma, as long as gamma is strictly less than 1, you'd still have a fixed, at most a fixed number of points that depends on gamma, but is independent of R. So this conjecture seems to be difficult even for gamma equals 1/2. And what I proved with Bartek is that if you look at the circle, there is a hope to improve on the 2. Remember, for d greater than 2, I made a point that you have to work with the L2 moments. Well, for the 2-dimensional case, I mean, it seems possible that in fact you could use any moments, not just the second or fourth on the left. And the 4th-dimensional estimate would follow with even minimal decay for the Fourier transform, if you can do a little bit better than Cordoba and Ciprian, if you beat the 1/2 threshold. Anyway, so it's a cute little problem that I thought I would mention. So in light of the results for the sphere, it makes sense to try to understand the paraboloid. Traditionally speaking, in Fourier restriction, we view the sphere and the paraboloid as very, very similar objects. Okay, the paraboloid behaves a bit better from a technical standpoint because it rescales very canonically, but both hypersurfaces have similar principal curvatures, and one might think that that they have a very similar theory. There's divergence when it comes to discrete questions, discrete restriction questions, when the lattice points are, or when the measure on the paraboloid or the sphere is concentrated on lattice points. So here's the definition of the paraboloid and the definition of the associated exponential sums. There is additional motivation to understand their spatial restriction to some manifolds, and this comes from the fact that these sums are solutions to the free Schrödinger equation on tori. Okay, so Bartosz and I made this conjecture, which is very, very similar to the one made by Bourgain and Rudnick. If you have a real analytic hypersurface with non-zero curvature, then the L2 norm of these exponential sums would have to be dominated by the L2 norm of the sequence. I'm not sure about the inequality on the left. I'm not sure if it's true or not. Honestly, we haven't spent too much time thinking about that part. But we mostly took this as an exercise, partly out of frustration of not being able to say too much about the sphere, and also hoping that the paraboloid is an easier model. We actually managed to verify this estimate for d equals 2 without any loss in n, and also with a log n loss for d equals 3, using only the decay of the Fourier transform of the measure. So we were not really able to do anything as sophisticated as Bourgain and Rudnick. Part of the difficulty comes from figuring out this normal form expansion for the paraboloid. But everything that we proved, including the log n loss in d equals 3, is fairly easy. I mean, it boils down to estimating the spectral norm of a matrix, and then use elementary methods without any number theoretical sophistication. It is also probably the case that this argument doesn't really need the points to be lattice points. It works as well for just separated points on the parabola and the paraboloid. And it's quite likely, as in the case of the sphere, that for higher dimensions, one would have to use some number theory. So I think it's a good problem if anybody is interested. Good. So these are the two examples that I could describe in a bit of a hurry, and I'd like to spend the rest of the talk describing the case of the moment curve. So if there are any questions before I move on, I'll be happy to listen. Alrighty. So the moment curve. The case of the moment curve came as a pre-natural continuation, if you want, of the previous two examples. And there has been some previous work by Chen and Sparlinski in the last 2 years or so regarding such estimates for the moment curve. They were mostly in partial ranges and motivated by applications to other problems. So we ended up running a more systematic analysis of these exponential sums, setting up the conjectures, proving sharp results in the full range in low dimensions and so on. And this is part of what I'd like to describe on the next few slides. So the exponential sum that I like to play with is defined at the top of the screen. Notice that I'm dropping any upper script notation. I'm not going to try to write a notation for the moment curve over there, because from now on, as I said, it's just the moment curve. All right, so there's an important exponent that I think most of you are familiar with. I can call it the Vinogradov exponent in d dimensions. It's d times d plus 1. What's the role played by this exponent? Well, there is a critical estimate. I'm not sure exactly how to call it. I'll call it for short VMVT, Vinogradov mean value theorem. I think Trevor would perhaps insist on calling it more like the main conjecture in the Vinogradov mean value theorem. So in any case, what it gives you, it gives you sharp estimates up to the n to the epsilon losses for the LP moments, is any number greater than, could go greater than 0, but I'll think about greater than 2. And so these have been proved by Trevor about 6-7 years ago in 3 dimensions, then by Bourgain, Larry Guth, and myself in higher dimensions, reproved by Woolley after that. And they are very satisfactory for many reasons. On the one hand, they do give you square root cancellation. So you see the L2 norm, little L2 norm there. So this square root cancellation in this regime. And for p greater than the critical exponent, this estimate is also sharp. You can test it with constant coefficients or coefficients of constant magnitude. All right, so given the fact that we understand everything when it comes to the Lebesgue measure, it makes sense to investigate the question about the moments of these exponential sums restricted to curved hypersurfaces. And all I'm going to need is non-vanishing or non-zero curvature. And the elliptic paraboloid that I had on the slides earlier, that has all the principal curvatures positive, but you could have hyperbolic paraboloids such as z equals x squared minus y squared in 3 dimensions. And those guys have one positive and one negative principal curvature, so they would still fall under the scope of this conjecture. And after testing with a few examples, we felt, courageous enough to make this conjecture. That's at the bottom. The estimate looks very, very similar to VMVT. There's only one notable difference, and that has to do with the critical exponent. It has to be PD minus 1, which is D minus 1 times D, and I'll explain why. But before I get there, you might remember some of the questions that I asked at the beginning of the talk, and one of them had to do with such a comparison. So is it possible that that the mass of the exponential sum concentrates on a manifold in such a way that the left-hand side exceeds the right-hand side? Well, this says that the answer is no in this regime, and that's fairly easy to see. If you look at the top of the screen, this estimate here, when p is less than PD minus, well, when p is less than PD, this estimate here is in fact an asymptotic equality if you allow yourself the n to the epsilon losses. That is because p being greater than 2 also allows you to do the lower bound, right? So in fact, this shows the L2 norm of the exponential sum is comparable to the L2 norm of the sequence. If you raise it to the power p, you find an equivalence. So we know that the left-hand side here is roughly of the size of the L2 norm of the sequence, and this explains this inequality. Okay, so it's one way of looking at the conjecture. So why is there a drop in dimension? Or it feels like almost as if there is a drop in the dimension, because conjecture 1 has PD minus 1 as the critical exponent. I'm going to try to explain the numerology in two ways. The first way goes as follows. Let me cheat a little bit and take a hypersurface sigma, which is not curved. I'm going to take a hyperplane, the horizontal one. The surface measure will be just the Lebesgue measure in the d-1 dimensional torus. Let's have a look at the p that's less than the critical exponent. Using the formula for the surface measure. Yeah, so okay, so let me start over from here. I was trying to explain the numerology on why is the critical exponent for this problem p equal to pd minus 1. And the one possible explanation is that perhaps curvature would not matter. Let's have a look at the case when the hypersurface sigma is equal to a hyperplane, the horizontal one. The surface measure is d sigma equal to the Lebesgue measure on the d-1 dimensional torus. And then, you can rewrite the LP moment on sigma with respect to this surface measure as an LP moment for the same exponential sum, except that now you have dropped the last coordinate, and you're now integrating with respect to this Lebesgue measure. So you see what happened, right? The d sigma became a Lebesgue measure, and since we have the Vinogradov mean value theorem, we can estimate that second term by the L2 norm of an precisely when p is less than pd minus 1. Pd minus 1 is the Vinogradov exponent for the d-dimensional moment curve, so we are in business. So if you believe that curvature should not be relevant for this conjecture that we have proposed, then if it's applicable to all surfaces, then it should be applicable to the hyperplane, and then in that case it has to be PD minus 1. Maybe it's smaller than that, maybe there's additional counterexamples, but you can't go higher than PD minus 1. How are we going to approach the conjecture? I'm going to give you some details in a few minutes. One thing I would like to say is that we never use the oscillatory part of the measure. We only use the decay of the Fourier transform, which is power decay d minus 1 over 2. I think using any attempt of using the oscillatory part seems like very, very complicated endeavor. It has to be perhaps a different method, and I don't want to speculate now, maybe a bit later in the talk.
Ciprian?
Yeah?
Why do you think that curvature should be irrelevant?
Irrelevant?
Mm-hmm.
Well, perhaps because of this example, right? So it works for this hyperplane, right? So we do prove, I mean, this is a proof of the conjecture in the case when the hypersurface is the hyperplane, the horizontal one. And there is another explanation. I think you didn't hear this explanation. It was during the minutes that we missed. If you look even at the Bourgain-Rudnick paper, the case of lattice points on the sphere, they make the same observation. They prove results for measures which are curved, and there is an observation conveyed to them by Peter Sarnak, which says that in the case of the circle, right, so d equals 2, the circle in 2 dimensions, the circle is in R2, even in that case, it seems possible that you can estimate the L2 norm of the eigenfunction by the L2 norm of the sequence when the hypersurface is flat. Now, what is a flat hypersurface in T2? It's a line. Except that in that case, the estimate you want to prove boils down to the Cordoba-Cileruelo conjecture about the number of lattice points on small arcs. So if that conjecture is true, then you can extend the Bourgain-Rudnick estimate in 2 dimensions to the non-curved case. Okay, so it's possible that the flat case, okay, hyperplane is an easy flat case, but there are all sorts of intermediate cases, nearly flat, partially flat, and so on. It's possible that if the conjecture is true in those cases, it will involve more delicate number theory, counting arguments of all sorts. I don't know. I don't want to speculate.
Thanks.
Sure. Okay, so let's move on. There's another way of seeing the sharpness in conjecture 1. Sharpness as in y is the critical exponent equal to PD minus 1. And I will illustrate that by showing you a particular type of hypersurface, right? We haven't really talked about sophisticated examples, but there is this example that fits perfectly in this cube, inside the cube QDN. What's special about this cube? It lies inside the d-dimensional torus, and it is the cube where the exponential sum associated with constant coefficients equal to 1 experiences constructive interference, in the sense that the whole sum doesn't have significant cancellations. The whole sum is roughly of magnitude n. Right, now how are you going to fit a curved hypersurface inside this box? it turns out that there is a canonical way of constructing them. X1 squared, the parabola, works in 2 dimensions, the hyperbolic parabolid, x1, x2 that I mentioned earlier, that works in 3 dimensions, and then you work your way all the way down the hierarchy by combining these types of examples. And if you estimate the exponential sum associated with the sequence 1, as I said, S is roughly of magnitude n. Then you look at the surface measure of sigma, of the part of sigma that fits inside this box. That's easily seen to be the product of the first d minus 1 coordinates. It's 1 over n times 1 over n squared and so on. And you compare the L2 norm with this estimate, and you get exactly what you want. Now, how do we approach conjecture 1? As I mentioned earlier, we approach it in a general way. We only care about the fact that the measure sigma, we don't care about the support of sigma. We don't care that sigma is supported on a hypersurface anymore. What we care about is the fact that its Fourier transform has this decay. And in this case, if we look at the LP moment, and notice that I have the d sigma on the left, but now I integrate on the torus because I don't know how the measure is spread out. Then I get a similar quantity on the right, except that the critical exponent changes. In 2 dimensions, if you compare, remember it's PD minus 1, so that's why I have P1, right? In 2 dimensions, the critical exponent was P1 for conjecture 1. And it happens to match the critical exponent for this new conjecture. They are both 2. So is the case in 3 dimensions. That's interesting. And then in 4 dimensions, there's already a discrepancy, right? The conjecture 1 is supposed to hold all the way up to 12. But now, since we're only using Fourier decay, row 4 is 11, and then this discrepancy increases as you increase the dimension. So row 5 is 18, which is less than P4, less than 20. Okay, so that means that there's no way we can solve conjecture 1 in dimensions 4 or higher, but we can still say something about conjecture 1. And our work is mostly about conjecture 2, which is in itself, asking some interesting questions. What can you say if you only assume the decay of the Fourier transform? So here's the conjecture 2 again. And how do we approach this conjecture 2? Well, we approach it via conjecture 3. These are all conjectures that we have made. If they are false, it's our fault. But we believe there's a reasonable case for at least the numerology to be right. So conjecture 3 looks fairly different. It's also about LP moments of the same exponential sums, except that we replace the singular measure d sigma with the Lebesgue measure dx, and we replace the full torus with a subset of the torus, namely a cube of length to the minus j, and then there is that weight on the left to the j d plus 1 over 2, but the critical exponent doesn't change. It's the same rho d, and it's the same estimate on the right. Now, I'm going to show on the next slide why, if you have an estimate like in conjecture 3 for an even integer p, then that implies estimate 1, right? It's a bit counterintuitive because you go from something that's non-singular to something that's singular. And the bottom line is that whenever the critical exponent rho d happens to be even, and this is the case 3 out of 4 times, it's even, it's an even integer, in fact, whenever d is not divisible by 4, then we can use conjecture 3 to prove conjecture 2. All right, so at least we have a strategy, a clean strategy, clean path to proving conjecture 2. So how do you prove that conjecture 3 implies conjecture 2? First of all, you have to run the dyadic decomposition. You look at the Fourier transform of the measure, you split it into the little Paley pieces. All we are using is the fact that each piece, being localized with a spectrum in an annulus, has the prescribed decay. And then we switch back, we dominate this by characteristic functions of annuli, or actually cubes if you want. And we use the Hardy-Littlelemma. I call it Hardy-Littlelemma. I wasn't sure, maybe somebody from the audience can educate me. I wasn't sure if there was anybody before them. It'd be a bit of a stretch that have used such a result. But I think it's in one of the joint Hardy-Littlelemma papers. And the lemma says the following: you have an exponential sum, and you use that on the left, you use the one with the positive coefficients on the right. Then you have two measures, let's say positive, and you have a subordination on the frequency side. And assuming that p is an even integer, then pretty much for every exponential sum, is completely unimportant here, you can dominate the left-hand side by the right-hand side. The proof of this is immediate, exactly how you expect it. P is even, you expand, you count, and you get it. But here's the catch. It's one of those arguments where where something works very easily with for a specified set of values of p, in this case even integers, and you wonder, do we miss a more difficult argument that covers also the other p's? The answer is no. So there has been a conjecture, I think it was called the Hardy-Littlelemma conjecture, that was open until Ben Green and Ruja disproved it for p equals 3, and then about the same time, I think it was Schlag and Mockenhaupt that disproved it, in fact, for any real number strictly greater than 2 that's not even an even integer. And the counterexamples, in fact, work even for the Lebesgue measure. Now, in our case, again, we can prove that conjecture 3 implies conjecture 2 when we deal with even exponents. I still feel conjecture 3 is much more robust and more general than conjecture 2. So there should be a different way of going between 3 and 2, but I don't know about that. So let me tell you what this implies in our case, or perhaps I'm gonna speak to the number theorists for a minute and compare this conjecture 3, which is now listed at the top of the screen. I'm going to compare it with what I call a hard conjecture. Okay, hard is really doesn't give full justice to this conjecture. It's about incomplete exponential sums, or non-translation invariant, if you want to call them like that. If you have a bunch of positive exponents beta, you cook up the exponential sum with those exponents, and then the conjecture says that, where's my critical exponent? Actually, it's formulated for all p. You can read the critical exponent from the estimate on the right hand side. The critical exponent p would be twice the sum of the coefficients or of the exponents beta. And I'll illustrate this with two concrete examples on the next slide, but I will just say that when D is odd, if you take the hard conjecture for granted, which you shouldn't because it's far from being solved, and if you use P equals rho D, which is what I just said, then you can get the conjecture 3. Right, so it feels easy, except that it isn't. So here's again conjecture 3, and the two examples that I promised are as follows. Conjecture 3 would follow when D equals 3 from the estimate about the L6 estimate about the cubes. This is open. I don't remember, there's a best known bound, certainly not epsilon, but sums of 3 cubes are always complicated. Some of the people in the audience know what I'm talking about. When D equals 5, conjecture 3 would follow from another estimate at a critical exponent. You see an L18 there. 18 is what I want. Row 5 is 18. And why 18? Because it's 4 plus 5 times 2. However, that second estimate is also very difficult. Now, interestingly, while both of these estimates are out of reach at the moment, we managed to prove conjecture 3 for D equals 2, 3, 4, and 5 using a different approach that is called small cap decoupling. I'll say a few words about that. Now I say I have reached my time. Can I take a few more minutes?
Of course, you can take 5 more minutes.
Thank you. Yeah. I think that's all I need. So as a result of proving conjecture 3, just to summarize, we have 2 corollaries. The first theorem is about conjecture 2, and we do verify conjecture 2 in 2 dimensions, in 3 dimensions, and interestingly also in 5 dimensions, and that means in the full range. And for conjecture 1, which is the hardest, there is a bit of a gap. We still reach, for example, so we proved that conjecture 1 in 2 and 3 dimensions. There is a larger gap in 4 dimensions, and in 5 dimensions the gap is a bit smaller. And I'll use the last few slides to discuss as a case study the D equals 4 case. So at the heart of our approach for conjecture 3 lies this idea of a small cap decoupling. Very briefly, what this means is that you have a manifold, in our case, the 4-dimensional moment curve, and you want to study how different pieces of that curve interact with each other, except that in the case of the Vinogradov mean value theorem, the arcs on the moment curve are big. Now you want to make them smaller. Or a different way of putting it is you want to perhaps keep the arcs of the same length, but you want to integrate or study the oscillations on a smaller spatial ball. And this is just one example. I don't think it's the time to get into any details. There's a result that we prove for arbitrary real analytic functions, just subject to various non-degeneracy conditions. And it's a very sharp result in the sense that the intervals omega I cannot be taken to be smaller. Even the little L6 coming before L12 is sharp. But okay, these are all details that I don't plan to talk about. Now, once you have such a result, I'll give you an idea about a corollary. You can test this result with phi 2 equals t cubed, phi 3 equals t to the 4th, phi 4 equals t squared. And if you plug in these functions and make the change of variables, then you get a certain square root cancellation for the exponential sum associated with the Vinogradov curve in the corollary, except that the intervals over which we integrate are small. They are no longer equal to the full interval 0, 1. Okay, so that's the idea of a small cap decoupling. You no longer have the periodicity interval associated with the exponential sum. You take it to be a bit smaller. What do you do with such a corollary? So here's again the corollary. Well, let's say I want to prove that conjecture 3 in a hurry, and maybe I want to prove it in a certain range. There is the scale parameter 2 to the j that varies between pretty much 1 and n to the 4th. Let's say I focus on the range n to n squared. Small cap decoupling would really take advantage of the small size of the integration, of the domain of integration in a smart way. So we want to understand how the oscillations occur, and I don't know if I want to read this slide, but for various variables you replace the small interval with 0, 1. For others you keep track of the smallness. You change variables, or perhaps you don't because the corollary already has the variables changed. And yeah, everything adds up at the end of the argument. The last line it gives you 2 to minus 5j over 2, which is what you really want. Right, and here's the last slide, which is very easy to read. I want to point out that this is a vast area. It's somewhat new. I mean, there were explorations, but they were not very centralized. And I think there's a lot more to be learned about variants of the problems that I have described. One of them, just give you an example, is the following. What if you consider slower Fourier decay? And what if you are interested in proving scale independent results, very much a la Bourgain and Rudnick? Well, we were able to prove such a result in L4 for the moment curve. If you go with the decay of beta equals 2/3 or higher, which is a bit less than asking for beta to be 1, the d minus 1 over 2, then there is a scale independent estimate in L4. Remember, the critical exponent is 6, so we can't really prove the result for L6 without the n to the epsilon losses. And this is more complicated than one might think. It is a counting argument, but it's a very delicate one, and for some time we were trying to see if such an estimate, for example, would be implied by existing results in the literature. We were trying to gauge the strength of such a result, but it turns out that the small scales, the small to the j's, are very tricky. And just to give an example, so the answer is no. I mean, I don't know of a way using something in the literature to get to such a result. Here's another example of something that something that's not known. It's not known even for p equals 4 that the cubes have a scale independent bound. And if you knew something just, I think, slightly better than 4 perhaps, then you could prove the result at the top. But why is this problem 4 complicated? Well, it's because of deep results in number theory. I only cite Silverman. It says that there is a sequence of scales as k going to infinity, such that there are more than O1 solutions to the equation m cubed plus m cubed equals sk. And these solutions are quite exotic, and it's a complicated problem about elliptic curves, pretty much, that makes this whole discussion rather difficult. All right, let me stop here. Sorry for the technical problems. I'll be happy to answer questions either now or later in the breakout room.